Welcome to the demonstration of a low latency bandwidth allocation mechanism for mission critical applications in virtual PONs with P4 programmable hardware. The authors are Diego Rossi Mafioletti, Frank Sline, Robin Giller, Michael O'Hanlon, David Coyle, Brendan Ryan, and Marco Ruffini. In this presentation, we provide a real-time demonstration of a low latency PON DBA mechanism, which is optimized for virtual PONs. Our implementation mixes P4 programmable data plane and software-based virtual DBA to provide efficient fast-track allocation for low latency applications. We demonstrate the concept and implementation of a DBA scheduler that is split into two parts, one that can run on a P4-enabled network card, and another more complex one which runs on a general-purpose processor. The combination of the two into our fast intercept mechanism provides the critical trade-off between speed and flexibility, as both data plane and virtual DBA scheduler have a high degree of flexibility. Our demonstration is of interest to a wide audience, including attendees interested in optical access network technology, network functional virtualization, and software-defined control plane operations. Attendees of the demo will witness innovative interaction between P4 DPDK in a push-pull configuration with packets bypassing the kernel network stack but are processed by user-land VDBA applications. The use of passive optical networks is a cost-effective approach for the delivery of ubiquitous broadband, since costs and capacities are shared across multiple endpoints. However, upstream scheduling requires a dynamic bandwidth assignment mechanism which operates through a report grant mechanism such as in ITU standard XGS PON. While it's much more efficient than static bandwidth allocation, it introduces a latency of several hundred microseconds, which becomes an issue for applications requiring end-to-end delays of 1 millisecond or less. This latency is further exacerbated when PONs are implemented as virtual network functions in modern implementations such as SDN-enabled broadband access, also known as SEBA, and when using virtual DBA. While these bring the required flexibility to fully customize a PON for high-performance multi-service and multi-tenant operations, the physical separation between hardware transmission equipment and software scheduling algorithms can further increase upstream latency. When the PON is used to provide low-latency front-haul services to Cloud RAN, DBA latency issues are solved by coordinating the 5G RAN and PON schedulers through a cooperative DBA algorithm. In cooperative DBA, the distributed unit, also known as the DU, in the RAN provides the ONT DBA scheduler with advanced scheduling information of the packet arrival at the RU connected to the ONU. This enables the OLT to send the ONU a transmission grant that is available as soon as the wireless data packet is received by the RU/ONU, thus minimizing upstream latency. However, if the PON is used to carry data from an application that requires low latency, for instance, in the instance of cloud robotics, where the packet arrival at the ONU cannot be determined in advance, latency cannot be determined by mechanisms such as cooperative DBA. In this paper, we demonstrate a mechanism to significantly reduce PON latency in these second types of use cases when the application level packet arrives at the ONU is unpredictable. The conceptual idea was already introduced in our previous paper. The idea is to split the upstream DBA scheduling into two parts. The first part operates according to the standard DBA procedures, where the bandwidth map is calculated after all required DBRUs are received for a given cycle. A second mechanism, which we call fast intercept, runs in the P4 hardware NIC, spoofing upstream low latency DBRU requests and storing them until the next bandwidth map arrives from the downstream frame. It then modifies the bandwidth map, adding grants from the low latency DBRUs on the unallocated portion of the bandwidth map. The downstream frame with the bandwidth map is then forwarded to all the ONUs following normal PON operations. The demonstration shows how this method, which is compatible with fully disaggregated PONs, can reduce latency compared to standard DBA operations, as the low latency allocations are assigned through a bandwidth map in the first available downstream XGEM frame. This mechanism is also much more efficient than fixed capacity allocation, as the dedicated capacity for low latency applications can be shared across all ONUs and is dynamically adjusted at every frame. This demonstration shows the latency performance improvement of our fast intercept mechanism on a virtual PON compared to standard DBA operations. Here we show the physical setup with a server used to generate DBRU requests at 10 gig line rate, emulating multiple ONU operations connected by an Intel X722 10 gig NIC to the virtual OLT, which hosts the P4 programmable smart NIC. Here, two processes generate DBRU for normal traffic and low latency traffic respectively, running on a DPDK packet gen traffic generator. These are intercepted by the P4 algorithm running in the smart NIC. In the figure, we can see that the normal DBRU are relayed to the host processor for DBA calculations. The DPDK VDBA runs over a QEM hypervisor accessing the smart NIC virtual functions via SRIOV. A single instance of the VDBA application runs on the system based on the Intel DPDK software version 2011, which runs on a 8-core 2.3 GHz Intel Xeon processor server with 64 gigs of DDR4 DRAM. Note that since this demo focuses on the scheduling algorithm, we don't implement a burst mode receiver at the OLT. Thus, the XGEM frames from the OLT are encapsulated over Ethernet before transmission. In this slide, we see the two paths of the standard DBRU and bandwidth map packets, and that of the DBRUs for tagged fast intercept. We distinguish the paths using the points A to F in the architectural diagram. At point A, the DPDK virtual ONU traffic generator creates upstream XGEM frames with DBRUs at line rate, that's 10 gigabits per second, tagged with a timestamp value and injecting them into the physical device of the X22 network interface card. At point B, the XGEM frames arrived at the Metronome Smart NIC physical interface, where a P4 program checks and stores low latency related DBRUs to be used on fast intercept mechanisms. If a low latency TCONT is detected, it goes through the P4 fast intercept mechanism, which will merge the low latency requirement into the current or next bandwidth map generated by the VOLT DPDK software. At D, all XGEM frames are forwarded through the VOLT DPDK application, which will calculate a new bandwidth map based on the DBRUs that are arriving. At E, when the bandwidth map goes down to the Metronome Smart NIC, if a low latency DBRU arrives at the Smart NIC, the P4 fast intercept mechanism merges it with the bandwidth map, changing the start time and grant size fields to accomplish with the low latency requirements. Eventually, at F, XGEM frames return to the DPDK virtual ONU traffic generator, which will collect the timestamps and all data collected from the packet. This shows the statistics on the screen and exports the latency data to be plotted using a graphical interface. Here we see the demonstration scenario screen. On the left is the virtual ONU traffic generator, and on the right is the virtual OLT performance screen. Traffic has been generated and received at 10 gigabits per second. Within the VONU pane, there are stats for upstream and downstream packet gen traffic. We can see the latency based upon the timestamps, the DBA session information, packet size information, and customized packet types. Within the VOLT pane, there are stats for DBRUs received, bandwidth maps generated, and there are controls provided for adjusting the complexity of the VDBA or path length between P4 data planes and the virtual DBA. We look at the timing results of the DBRU and subsequent bandwidth map generated traveling through the full path 8F through the host D. Looking at the statistical sample of the round-trip times, we see on average the duration is 180 microseconds as shown in the top blue line. This includes a DBA complexity and placement penalty of 130 microseconds. For the demonstration, this graph is updated in real time. Next, we look at the timing results of the DBRU and subsequent bandwidth map generated traveling through the path 8F through the fast intercept path C. This is accomplished by clicking a software switch to turn on fast intercept for particular TCONs. Looking at a statistical sample of the round-trip times, we see on average the duration is 37 microseconds as shown in the lower red line. For the demonstration, this graph is updated in real time. So, in closing, we've highlighted an opportunity for the principles of fast intercept, where cooperative DBA is not appropriate, for instance, for aperiodic traffic. We've constructed an architecture to prove and test the principles of fast interception. We have demonstrated the principles of fast interception, contrasting performance against the traditional DBA path through a host. We acknowledge that fast intercept is a blunt tool without the granularity and bandwidth efficiency of more complex host-based algorithms. We foresee that the next steps are to test in more real-life scenarios, particularly with tactile and haptic or URLLC scenarios. Thank you for your time and attention.